Hello everyone, my name is Aziz, and for for this seminar in Advanced Sensor Engineering, I'd like you to present the ultrasonic sensor. Its physics, structure, design, operational principle, and so on. So the table of contents of this presentation will be as follows. We'll briefly talk about what is ultrasonic sensor, its features, principles, topologies, and the factors that may influence to the sensor. And at the end, we'll make a summary. So let's start. There are many creatures in the earth that tries to use the sound as a way to catch their prey. In this particular example, we have a bat and dolphin that use echolocation to estimate the distance to their prey. People try to imitate this concept by biomimicry and create devices such as ultrasonic sensor that make this possible. So what is an ultrasonic sensor? This is a physical device that determines the presence of an object or measures the distance without making any physical contact. Ultrasonic sensor sends ultrasonic waves from emitter, as you may see here, and receives the reflected wave with the detector. And then the sensor captures the difference in time between the emitted and received echo. So we may say this is round trip time, and we calculate the distance. And this is very simple formula. We have the round trip time. We multiply with the speed of sound and divide it by 2 to get the distance one way from this sensor to the target. Now let's talk about features of ultrasonic sensor. First, color do not influence the detection. It can detect the shiny, flat objects, and transparent objects will get the same performance. It is good for difficult shapes, and independently of color and the structure, it performs very well on detection. In addition, it can detect the objects in a wider area. In comparison with photoelectric sensor, they can check the wide area at the same time. And important thing to mention here that the sensor is non-contact. Therefore, the sensing objects no need to be touched in order to be detected. Therefore, they won't be scratched. Talking about operating principle of ultrasonic sensor, this is transducer that uses electrical energy to generate ultrasound waves, and at the same time it converts the ultrasound vibrational energy into electrical signal. And here is architecture of ultrasonic sensor, and as you may see here, we have a piezoelectric ceramic here that will be used for transmission and reception. When we transmit the signal, piezoelectric ceramics generate electromotive force between the electrodes that is proportional to amount of mechanical force applied to the element. So basically we vibrate this element here to generate the waves that will propagate forward. And while receiving the reflected waves back, the air compression occurs and mechanical displacement is generated that is proportional to that voltage. So basically the reflected waves that will come back and hit the ceramics will generate mechanical displacement. By measuring this displacement from the magnitude of electromotive force, the presence of an object is detected, and we can estimate the distance from the sensor to the object. Ultrasonic sensors may have different topologies. One is monostatic topology, when a single transducer both it transmits and at the same time it listens for returning echoes. And it's most widely used in the industry because of its low cost. And here is the example of monostatic transducer. Second type is bistatic topology, when there are two separate transducers. One transducer transmits the signal to the target, and another one, we may call it as a receiver, it receives the reflected waves back. So the drawback is that additional calibration is required in this particular case, because we need to consider the angle of the incoming echo at the receiver based on the distance and detection range. And here is illustration of bistatic transducer. Maybe this is sensor is very familiar, because in Arduino a lot of people use this type of sensors. Let's talk about factors that influence sensing. First, this is transmission medium. Transmission properties of the speed of sound changes across the mediums. Let's say speed of sound in the air is 331, but in the steel is much more higher. Next thing is acoustic impedance. We can define it as a product of density and acoustic velocity. Let's say air has much lower acoustic impedance in comparison with the liquids and solids. And the important here is that the greater the impedance mismatch between two mediums, the greater percentage of energy is reflected back. So we have here two examples. Here we have the transducer that provides 100% energy to the target, and in case of the skin and air, we have 99% of the energy reflected back, because we have reflection coefficient of 0.99, because the greater impedance mismatch between the skin and air. However, in case of the steel and water, the reflected energy consists of 88% of original. Factor to consider is radar cross-section. The radar cross-section is how well the target is able to reflect ultrasonic waves back to the transducer. Let's say curved objects like this, or tilt objects, may have scattered the majority of this ultrasonic sound transmit towards the object, where the flat target has a good response back to the receiver. So the surfaces that yield the strongest echo response, these are large, dense, and flat and smooth objects. So basically we can compute this by projected cross section, by the product of projected cross section, reflectivity, and directivity. And another factor that influences the sensing is ambient conditions like temperature, humidity, and debris. So as I mentioned, the velocity of the echo is influenced by external environment parameters like temperature, humidity, and the sensing range decreases when the temperatures increase. And although the sensing rate also decreases as the humidity increases, this can be neglected because the effects are minimum. So we may say the rate of attenuation across the temperature and humidity is not linear, and one of the ways to compute is provided as follows here. And comparing the ultrasonic and other sensing technologies such as infrared, optical, and radar systems, the infrared technology it's pretty good. It has a high resolution, low cost. However, prior implementation, you need to know the surface properties. Talking about the optical based sensing technology, it has the same technology as the ultrasound, but instead they use the light. It works good, but in foggy and smoky environment it shows the bad performance. Talking about the radar systems, they have high precision. However, in terms of cost, it's much more expensive than these technologies. Therefore, the ultrasonic sensor has it has a wide field of view. It is relatively low cost, and yes, it can effectively detect solid and transparent glass surfaces and work in a smoky and gas-filled environment. To sum up, ultrasonic sensor is a physical device that determines the presence of an object or measures the distance to an object without making any physical contact. It is transducer that use electrical energy to generate the ultrasound waves, and at the same time it converts ultrasound vibrational energy into electrical signals. The operation principle is based on piezoelectric ceramics that are used for transmission and reception. The factors such as transmission medium, the impedance, radar cross-section, and other ambient conditions highly influence the performance of the sensor. However, ultrasonic sensor showed great potential advantages among existing proximity sensing technologies because of its effective detection of a solid and transparent surfaces. So that's it for my presentation. Thank you very much for your attention.